Okay, let's do some calculations with universal gravitation, which relates the force that arises between two masses, or actually any combination of masses. The equation is, let me just get something to write with here. Force is universal gravitational constant, capital G, m1, m2 over r squared. And of course the r they're referring to is, if I have, say, two masses, it's going to be the distance between their centers, r. Okay, and capital G is actually equal to 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. Okay, let's try one of these. So 485 kilogram sphere sits at 14 kilometers due north of an 852 kilogram sphere. What is the force of gravity on the first sphere due to the second sphere? And compare this force of gravity on the second sphere due to the first sphere. Well, the third law will probably have something to say about that. So F is equal to G m1 m2 over r squared. So let's let this be the first one. This is our distance r, which it's in kilometers. We're going to have to convert that to meters. And this is our other sphere. So let's plug all that in. So 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. This is 485 kilograms. This is 852 kilograms. And we're going to divide all that by, now there's 1,000 meters in a kilometer, so this is actually going to be 14,000 meters, and that'll be squared. Okay, so let's see if we can work that out. So 6.67 to the minus 11th times 485 kilograms times 852 kilograms. Okay, you'll notice that's pretty small. That's actually the value of our numerator. And this is about to get a lot smaller because I still have to divide by 14,000 meters squared. So I'm going to divide by 14, let's see. Okay, let's try that again. Divide by 14000, and I'm going to square it, and that's going to be about 1.4 times 10 to the minus 13 newtons. Let me move me out of the way. 1.4 times 10 to the minus 13th newtons, or 0.14 picometers if you're familiar with the metric abbreviations. That's a really small force. Okay, that's a really, really tiny force. Let's try the next one. This one is with a couple of bowling balls, 2.5 kilograms each. A kilogram is about 2.2 pounds, so 2.5 is something like 5-6 pounds, 5-6 pound range. It says two 2.5 kilogram bowling balls are half a meter apart. What is the force of gravity of the first bowling ball due to the second, and compare this to the force of gravity on the second bowling ball due to the first. Oh, did we do this in this one? The forces are going to be equal and opposite. It's just that they're going to point in different directions. The first ball is going to have a force acting on it pointing back to the second, and the second ball will have a force acting on it pointing to the first. Okay, so for every action there's an equal but opposite reaction. That's what that means. Okay, so we have two 2.5 kilogram bowling balls. We write down the formula again, and we have 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, and 2.5 kilograms, 2.5 kilograms, all over 0.5 meters, and don't forget to square that. Okay, let's see what we can do about this. Okay, there's our problem from before. Let me clear out the history there just so that's not confusing. So 6.67 exponent minus, whoops, hit the wrong minus, 6.67 exponent minus 11 times, now each of these is 2.5 kilograms, and there's our numerator, really tiny. Okay, and we're going to divide that by 0.5 squared, which is equal to, well, it's equal to that. Let's get it in scientific notation. It's about 1.7 times 10 to the minus 9th. So 1.7 times 10 to the minus 9th, oops, newtons, because the kilograms divided out, the meters divided out, and it left us with newtons. Okay, so far so good? All right, let's try the next one. If we have a 112 kilogram man standing 551 meters from a building of 25,500 kilograms, what's the gravitational force between them? Well, it's the same universal gravitation. So 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. 112 kilograms for the man, and 25,500 kilograms for the building. And they're about 551 meters apart. We're going to square that, and that is going to give us, let's see what that gives us besides a giant headache. We're going to clear this, clear the history. So 6.67 exponent minus 11 times 112 kilograms times 25,500 kilograms. And because of the increased mass of the building mostly, we've got a number that's about 2/10,000ths in the numerator. The denominator is quite large, so we're still going to get a pretty small result. So we're going to divide that by 551 meters, and we're going to get about 6.3 times 10 to the minus 10th. So 6.3 times 10 to the minus 10th newtons. Don't forget the meters squared cancel, the kilograms squared cancel, leaving us with newtons. Okay, let's try the last one. So force is G m1 m2 over r squared. Our G, the universal gravitational constant, is the same. And we're just going to plug in the mass. First mass is 255 kilograms. Second is 895 kilograms. And the distance is 18 meters. And that's going to be squared. So let's see what we got. Clear out the history. Okay. So 6.67 exponent minus 11 times 255 times 895 equals. Okay, so we've got, oh, that's a problem. Okay, I know what I did. I forgot my negative exponent. 6.67 exponent minus, that's what happened last time. Okay, now times 255 times 895 equals. And I'm going to divide that by 18 squared, close the parenthesis, and I get about 4.7 times 10 to the minus 8th. So that's actually a little larger than our previous value. So 4.7 times 10 to the minus 8th newtons. Okay. And let me just pause for 1 second. Okay, so what I'd like to do now is I'd like to derive that G we got for the acceleration due to gravity on Earth, which was about 9.8 newtons per kilogram, or 9.8 meters per second squared. Now, a newton per kilogram is a meter per second squared because a newton is a kilogram meter per second squared. So if I have a newton per kilogram, it is a meter per second squared. Dealing with that just as if it were a fraction. So we already know that near the Earth's surface, weight is mass times gravity, that acceleration due to gravity. And we've just done a little bit with universal gravitation. And I'm going to say little m and capital M over RE, which is going to be radius of the Earth. So if this is a mass at the Earth's surface, given the acceleration due to gravity on the Earth's surface, this will be little m's weight. So weight is a force, and if this weight is actually this force, what we can do is we can set the right-hand equations here, the right-hand side of both equations equal to each other. And what I can say is that mg is equal to g, little m, big M, remember big M is the mass of the Earth, divided by the radius of the Earth squared. You'll notice that the little m divides out, and I now have an expression for the acceleration due to gravity. Let's see what I get here. So we have 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Mass of the Earth is 5.972 times 10 to the 24th kilograms. That is quite the size. And the radius is actually 6,371 kilometers. Since there's 1,000 meters in a kilometer, that's actually 6,371,000 meters. So 6,371,000 meters, and of course that's squared. So let's see what that could be. So one of the kilograms is going to go away, the meters squared is going to go away, and our units will be newtons per kilogram. So this is almost 6, this is over 6. We'll do it on the calculator. If this was all in scientific notation, I would estimate. So let's see. See what we got here. Let me get rid of that. This from the previous problem. And 6.67 minus 11 times, and mass of the Earth is 5.972. 5.972 to the 24th, and that's our numerator. Okay, and the radius is going to be 6.371 to the 6th. We're going to square that, and look at that. We get 9.8. I can't draw on here, but if you look at those first two numbers, that is exactly what we get. 9.8 newtons per kilogram, or the acceleration due to gravity on the Earth. Okay, so when we say G, weight is mass times gravity, lowercase g, it's 9.8 newtons per kilogram, because given the mass of the Earth and the acceleration due to gravity, mass of the Earth and the radius of the Earth, that's the acceleration due to gravity. Okay, so I hope that made things a little clearer. We'll take a look at, once you finish the video, take a look at the problem set in the Google form questions. They're actually pretty easy. Just do it step by step.